capability indexes and the defect probability, right? So that will help you with question 23 and 25 of the homework. And today we will need to move on to the next topic where that will help you with question 24 in our homework. So let me try to consolidate different acronyms so that we are totally clear about them. And then we move on to the next topic. All right. So remember, we're still in module 5 about quality management, right? Module 5, quality management. And last time we talked about the defect probability. Or DP. So I would like to clarify that whatever it is, DP or DPMO, I mean DPU, or the probability of being defective. So today we talk about the probability of being defective. They are all the same thing. We talk about the percentage or the proportion of errors, or the percentage or the proportion of defective or defects, right? So they are all the same thing. P, DP, DP, DPU, and PFD, right? And when we talk about these in the context of 1 million units, right, there are also different ways to call it. Last time we talked about that as a ppm, parts per million, right? And parts per million are the same thing, is the same thing as DPMO, or sometimes we call that as a EPMO. Especially in services, we talk about hotel errors, restaurant errors, or service errors, shipment errors, right? So in that case, we would like to call that as PEPMO rather than DPMO. But regardless of what we call it, they tell us the same thing. Why out of 1 million units, how many units are affected, right? Or with errors. Okay, and there's another concept that we normally use. It is called the sigma level. If you recall in the book, if you read about the process capability indexes or whatever, they calculate the capability indexes, and if that capability index is 2 or so, or 1 or so, it means that we can squeeze or 2. If the CP is 2, then it means that we can squeeze 6 standard deviation inside on one side of the design specification, right? So the sigma level that they use in the textbook is how many standard deviation that we can squeeze inside the spec limits, and the more the better, because the more means we'll have fewer defects, right, out of our process. But that sigma level understanding is kind of only for manufacturing, right? In this case, we try to make it a little bit more general so that we can talk about the sigma level of any company, company of any industry. It doesn't have to be in manufacturing. So the sigma level that we are using here is defined as norm dot as dot inverse 1 minus the DPU, right? DPU or DP or PFD, they're all the same. So it's just 1 minus the percentage of errors or percentage of defects, right? As a number. So this is a number, norm dot s dot inverse 1 minus the DPU. And then after we get that number, we would add with 1.5 separately, right? This dot right here is to dim, right? You make it bigger. So that's the equation of the sigma level. And after we calculate the sigma level, we can always draw or make a sketch of where it is, right? So this is a sketch of the sigma level. We would borrow the standard normal distribution like the following. So it's a symmetric bell-shaped curve like this. And somehow we cut the right tail so that the right tail equals the DPU or DP or PFD, whatever it is, right? So we cut it, and then we pin down that blue point right here. By the way, the mean is always 0. So this number here is a number greater than 0, right? So we cut the right tail so that that is DPU, and then we got that blue point. After we got the blue point, we add with 1.5, right? Then we have the red point. And the red point is our sigma level, right? And we want the sigma level as big as possible, because if we are having a big sigma level, then the DPU will be small. So high sigma level suggests that or signals that our defect probability is small, right? So that's why we want to have higher and higher sigma levels over time. So that's the for us to consolidate different things of different topics, right? They are all the same thing here. We talk about the same thing when we talk about the probability of errors or defects, right? And then the sigma level. This definition of the sigma level is very general. It doesn't have any industry in it. It doesn't have manufacturing or service. It means that it can be applied to anything as long as you calculate or have the percentage of errors or the percentage of defects, right? You put it here, and then that's it. We just go through the equation, and then we have the sigma level. Right. So that's what we have so far, and today we need to move on to the new topic. So let me share with you where you can find the new topic in the slide. Okay, so we have this on slide 17. This is near the end of the module 5. We're not done with the module 5 yet. It's just because question 24 is due next Monday. 23, 24, and 25 are due next Monday. So that's why we had to go straight to this topic so that you can work on question 24, right? So it's about the binary outcome. I'm sorry, that's slide 69, the first slide of this binary outcomes topic. So why do we talk about binary outcomes? For example, in the manufacturing process, they manufacture this keyboard right here, right? So I hope it shows the virtual background, make it kind of invisible now. It's tricky to show it, right? Okay, I hope you can catch a glimpse of it, right? Okay, so what is more important that I want to show you here is at the back of the device, there's a stamp, okay? Where's that thing? All right, here. You see that stamp? That's a quality control stamp. So every unit would go through some kind of testing, and if the unit is functioning well, perfectly, then they will put a stamp and pass it through and ship it out, right? But if the unit has some kind of defective aspects in it, it is malfunctioning, then that unit is deemed as defective, and it will be sent back to the shop for rework, things like that, right? So a lot of things that we see in real life are kind of only two possibility or two possible outcomes, right? Good or defective, right or wrong, things like that. So that can be applied to manufacturing, right? The keyboard that I just showed you is in manufacturing, but also it can be in services too. So at the end of the tour, we might ask the tourists, "Are you happy with our service or not?" Right? They might say good or not good, things like that. So there are two possible outcomes that we get from the end, right? So the binary outcomes here can be applied. Topic here can be applied to many things, as long as there are only two outcomes: good and bad, defective or good, right? So later on, we are interested in the probability of being defective, or the PFD, or the DP, or the DPU. They are all measuring the same thing, right? Probability of being defective. And we also want to know the probability of being good. As a manager, these two numbers are very important for you, right? We want to improve the probability of being good over time. We want to reduce the probability of being defective. And then to calculate these two probabilities, we will need to rely on the event tree. The event tree shows us the connection inside the situation, and it tells us the logic behind some outcome, good or defective, right? So in this case, we talk about defective and good. So later on, we would work on these two examples. The first one is the assembly operation example, okay? And then to do that, we have to draw the event tree right out here. And second, we're gonna go through another example about medication inspection. So it's a lengthy story right here, right? To make more sense of this long story, we would need to draw the event tree, and we would base our calculation on the event tree. So that's a heads up, and I would like to go back to the verbal. Let's talk about the background first, and then I will go back to the one of the examples that I showed you earlier. So earlier we talked about the probability of defects, but now today we move on to the new topic, where we calculate the probabilities of binary outcomes. Right, binary means two, right? So there are only two possible outcomes. So those are the binary outcome situations. Again, we are interested in the probability of the units to be good, right? So being good. And the acronym for that is a PFG. And also we want to know the probability of being defective. We would call that as a P of B. And here's the thing. We know that in this kind of situation, there are only two possible outcomes, right? So that's why the probability of being good plus the probability of being defective is going to be 100%, or 1.0, right? There are only two possible outcomes, good or defective. Then if we count all the good units, we add that with all of the defective units, and we cover 100% of all of the units produced through the machine or through the process, right? Okay. Again, it can be in manufacturing, but it can also be in services. So that's the probability, the probabilities that we are interested in. And to do this, we have to use the event tree, because it shows us the logic behind the outcomes. We say that outcome is bad or defective, or we say that outcome is good. Then why? We have to use an event tree to really understand why we say that as good, why we say that as bad, right? The connection in the situation that leads to a good outcome, or the connections inside the process that lead to a bad outcome or a defective outcome, right? So as a heads up, I would like to lay out here the two examples. So example number one that we need to go through is the assembly line. Right. This is module 5 and slide 70, I think. Let me check. Okay, so that's the first example. And the second example is the medication inspection. And this is module 5, slide 72. So that's that, or those are the two examples that we are talking about the next. And these two examples will help you with question 24 in their homework, right? So let me show you the first one. In the assembly line or in the assembly of a simple component, there are 3 steps that potentially can lead to defects. The first step makes defects in 2% of the cases. The second step makes defects in 5% of the cases. And the third makes defects in 3% of the times, right? In order for the component to function correctly, all 3 steps have to be carried out correctly. That is, a defect in any one of the 3 input variables will lead to a defect in the output, right? And what is the probability of being good, and what is the probability of being defective? So we don't have, we have the story, but we don't have any kind of specific context here. So I would like to kind of make up an example so that we can understand more about this example, okay? So for example, I want the switch, I need to replace the switch panel in my house. Then I will have to go to the Home Depot and buy a switch panel. And on that switch panel, there's 3 individual switches, right? Switch number 1 is for this device. This switch number 2 is for that light. Another switch is for something else. So there are 3 individual switches on the same panel. And to be a good panel, then all 3 switches have to be good, right? Because if only one is defective, one switch is defective, then I will return that unit to the Home Depot right away, and then I will exchange for a better unit where all 3 switches will work perfectly, right? So actually, that's the logic behind the story that we read here. They say that a defect in this sentence right here, that is, a defect in any one of the 3 input variables will lead to a defect in the output or the overall outcome, right? Because if we have 3 switches and one of them doesn't work, then of course the whole panel is defective. Nobody would like to keep it. They can easily exchange for a perfect unit, right? So, so here, and then at the end, we need to calculate the probability of being good probability of being defective, because as a manager, we really want to know this so that we can improve our process over time, right? Okay, so let's work on this example together. So we are still in module 5. We talk about the big topic of binary outcome. And in that topic, now let's talk about the first example. Where we talk about the assembly operation. In this case, let's talk about the 3-switch panel. You can try this example in slide 17. Right. Okay. So first of all, to understand the story, to understand the logic behind the outcomes, we should draw the event tree. Okay. So a unit will have to go through 3 stations. At the first station, they will put on the first switch. The second station will do the second switch, and the third station will put the third switch on the panel, right? So right now we are looking at the first stage right here, stage number 1. So at stage number 1, the outcome might be either defective or good. So we have the being defective right here and being good right here, right? So that's the outcome for the first individual switch on the panel. And now the unit continue its journey through the second station. So here is what might happen at the second station. The second switch might either be defective or good. And to be consistent, I always put the defective on the left-hand side and the good on the right-hand side. So being defective here, being good here, the defective here and good here, right? So this is might happen at the second stage. And then so we have defective or defective or good, depending on what happens earlier at the first stage. But either way, the second station is independent of the first station, or in other words, the outcome of the second switch is independent of the first switch. Okay, so when we're done with the first and the second stage, then the unit will have to go through the third stage, where they put another switch on. So that's station number 3 right here. Right, and then we would see the outcomes. So the units at station number 3 can either be defective and good. Again, we put the defective on the left-hand side, good, defective, good, defective, and good. All right. So right now we have a tree. We have the branches of the tree. It might look upside down, but if you flip the other way around, you're going to see that as it looks like a tree. Okay. In the book, they say that at the end we have the leaves, right? So the leaves are the outcomes right here, the overall outcomes right here, right? Is that defective or good, right? Earlier, we called this as an individual outcome, defect, good. These are individual outcomes. But out here, we call that as an overall outcome. And in this case, right, we want to determine if the overall outcome is good or defective. For example, we are looking at the first branch right here, and we ask ourselves, is that a defective unit or is that a good unit? So I would like to ask the whole class, what do you think about that question mark right there? Overall, is that defective or is that good? Should I write, if it is defective, of course, we're gonna return that to the Home Depot. If it is good, then we keep it and install that onto our house. Okay, you are very efficient. Good, you just give me the D. I understand, that's totally fine. Okay, so all of you say defective. And you are correct, right? Because the first switch is defective, the second switch is also defective, the third switch is also defective. So the whole unit, the whole panel, something like this, right? Something like this, where there are 2 buttons on it and all 3 are defective. So the whole unit is defective. Right, so in this case, we have a defective outcome down here. If it is defective, I would like to use the diamond to signify that it is defective. Later on, if we see a good outcome, we do the circle, right? The circle is a perfect shape, so we use a circle for the good outcome and the diamond for the defective outcome. I would like to ask the whole class what would be the outcome of that. I mean, is that defective or good? I see a lot of responses already. You overwhelm me. That's very good. I would like to thank you all for your active learning. You are correct. In this case, the first switch is defective, right? How do we know? We just trace along the branch right here. Right? We follow that branch. The first switch is defective. The second switch also defective. The third switch is good, but then in overall, the whole thing is defective, right? I would go back to the Home Depot and exchange for a good unit right away. I would not want to keep this at all because I want to turn 3 different things on. So all 3 switches have to be perfectly working, right? All right, so in this case, we're gonna have a defective outcome right here. But then earlier, we also have the defective outcome. So to make it clear, let's call this as a D1, and this is as a D2. Defective, the second possible defective outcome, the overall outcome that is defective. The third one is also easy, defective, good, and defective. Yeah, Sophia, yeah, fast. So in this case, right, if you look at the third branch, the third branch is right here. So you just trace it and you see 2 defective. And even though we have 1 good, but that doesn't count anymore, right? So we would have a defect overall outcome here. That's D3. The next one, okay, so we have 2 goods here and here. But then the first switch is bad. So the whole unit is defective, right? So we would have the D4 right here. Okay, and then the next one, we have, if we trace that branch right here, we have good, defective, defective.
I'm sorry, I have a question. For D4, you said because the first one is defective, it makes it all defective?
All right, so think about this, okay? I have a panel like this. I have a panel. This is a keyboard, but just imagine it is a panel. How to show it? It's very tricky with the virtual background. It only shows human faces. It doesn't show the object. Let me try, okay? Let me try. It's like I'm doing magic right now. How to show it? Oh, it doesn't show at all. Okay, so that's a panel where I have 3 buttons on it, okay?
Mm-hmm.
So if two button works and the third button doesn't work, then definitely this whole unit is defective.
Oh, okay.
I hope you see that logic, right?
Okay. Thank you.
Yeah, because all units, I mean, all components on that unit have to be good. Otherwise, the whole thing is not good.
Okay, thanks.
Yeah, so if you go to the Home Depot, you might see something like that. On the same panel, we might have different buttons. One is for the heater, one for the light, one for something else, right? So that's so that's the nature of the product. So at the fifth branch, we should also have another defective outcome here. We have good, defect, and defect, right? Then it should be defective. By the way, I would like to try you with this next one right here. Is that good or defective? Now I see two cans. Some of you say good, some of you say defective. All right. And who is right, who is wrong? All right, I agree. This is confusing. It's not straightforward because this got the first time that we learn something like this, right? So actually, this outcome right here, this overall outcome, is defective because even though we see the good right here, we see the good down here, right? But along the way, we also have another defect here. So the two buttons are good, but the second button, the first and the third button are good, but then the second button is defective, right? Then of course we don't want to buy that unit at all. Everything on that unit has to be good before we keep it. In this case, we're gonna go back to the Home Depot and exchange for a perfect unit, right? So the outcome here is defective. So now I hope that everybody see the logic in this tree diagram, right? It is a logical connection among different parts of the unit, and that will lead to the overall outcome. And of course, the next one will be defective because we have two good switches, but the third switch is defective. So that single defect will spoil the whole unit, right? Okay, and finally, if you look at the last branch right here, we have all good switches, right? So we have a good overall outcome. So the G is right. So that's the nature of the unit of the product that we have at the end, either defective or good, right? If it is good, we put a quality stamp and let it go and be shipped out to the customers. But if it is defective, we're gonna send back to the workshop. Okay. So as a manager, what we want to know next is the following: what is the probability of being good, and what is the probability of being defective, right? So I think that if I ask you that question, some of you might respond as the following: among the 8 possible outcomes that we see here, right? Among the 8 possible fruits that we see here, there is only one good fruit. So it seems like the probability of being good is 1 divided by 8, right? But you know what? That will be wrong. Why so? Because different branches will produce different fruit to different sizes, right? We have to account for the sizes of the branches. Some branches are small, some branches are big. We have to account for that relative importance of the branches. So if you look at the question one more time, you're going to see some numbers, some more information that they give. The first step makes defects in 2% of the cases. The second step makes defects in 5% of the cases, and the third makes defects in 3% of the cases, right? So with that, now we can determine the size of the branches. So they say defective 2% of the first stage. So I write that 2% here, right? And if it is 2% effective, then it must be that 98% good. So I just take one, subtract it, and then we have the other side of the stage. So defective and good adds up to 100%. So 2% here, 98% over there. The second stage makes defects in 5% of the time. So we put out 0.05 right here. And that means that the good is 0.95, right? And then the second switch is independent of the first switch. So we have 0.05 right here again, and then 0.95 here. Right, so that's the relative sizes of the branches. And if we look at the next number, at the third, we make mistake or defects in 3% of the time. So you would write that 3% right here. And then it means that the goods individual outcomes are 97.97, right? All of these are called individual outcomes, or the stage outcomes. But out here, we have the overall outcomes, right? It's different. So the overall outcomes are different from the individual outcomes. Okay, so see, you are very fast. You are right. So in this case, right, we as a manager, we want to know the probability of being good and the probability of being defective. And if we calculate the probability of being defective, right, you see that we have a lot of workload here. We have to calculate it many times and then add these numbers up, right? So the smarter strategy in this case is we would calculate the probability of being good first. And then we take one, subtract that, so that we have the sum of all of the defectives all together, right? So that's our strategy, and that's what we are doing next. And by the way, it's very similar to what you would do for question 24 of our homework. Okay, so we would calculate the good first, and then we take one, subtract it, right? The probability of being good, like C already shared, you are correct, is the following. We will need to calculate the probability of being good at the first stage. And the second stage also had to be good. So we multiply, right? This and that at the same time. Then in probability, you have to multiply the numbers. You cannot add the number. You have to multiply them. And then we would have the probability of being good, the third stage, right? So if you look at the three branches, so technically we are looking at this this branch right now, being good, right? So you look at that branch right now. So the first part here is 98, that's 95, that's 97 down here. So how do we know 97? Because remember, that's 0.3 on the left-hand side, 0.97 on the right-hand side, right? Everywhere. 97, 3% here, 97% here, 3% here, 97% there. So it means that we need to multiply these three numbers together, right? So let me go back. So we just multiply the three numbers that we see over there together. So we have 0.98 times 0.95 times 0.97, right? And the answer, okay, so see, you're correct. Let me give everybody the decimal answer. So that should be 0.90307, right? Or in this case, we talk about the probability of being good of 90.3%. Okay, so I would like to have your personal opinion on this 90.3%. Do you think that this is good or not good? We talk about manufacturing products, process, or service process. We have 90% good outcomes, right? What do you think about this number? Is that good or not good for you, personal judgment? Some of you might say good, some of you might say not good. All of the answers are valid because here I only ask for the personal judgment, right? Okay, so in the daily context, a lot of the things we see that 90% is a good number. But please keep in mind that it means that 10% are defective, right? We produce 100 cars and 10 of them, nearly 10 of them are defective. Not to mention if we produce like 1 million units, like nearly 10% of 1 million, which is nearly 100,000 units are defective. Right? Think about it, it is a huge number of defects, right? So yeah, I would say that it depends, but sometimes for this process it is good, for another process it is not good at all, right? All right, so the next step is, I appreciate all of the contributions. It's just a personal opinion, because sometimes you work for that company, that 90% is a good number, but when you go to another student works for another company, 90% is not a good number at all. Right? All right, so let's talk about the probability of being defective. Right, as a manager, we want to know it. So by definition, that's going to be the probability of B1 plus probability of B2, B3, B4, B5. You know what? I feel tired by writing this long calculation already. P of D6, P of D7, right? That's a daunting task right here. It means that we have to do what we just did earlier 7 times, not just 1 time. For each number here, we have to calculate we have to multiply 3 individual numbers, right? And now in total, we have to do 7 times of that. So it's a daunting task. So we can do better than that. So here's a shortcut. We know that the P of G plus the P of D equals 100%, right? So the trick is we do 1 minus the P of G. Then we're going to have the P of D. So the shortcut is we take 1 minus 0.90307. Then we would have 0.09693, right? Or we have about 9.7% defective. Nearly 10% effective. Out of 1 million units, we're going to have 97,000 units that are defective. Okay, so that's a number that we have to think about, right? So of course, in the homework question, I will ask you to calculate the ppm or the dpmo, so that we can say that out of 1 million units, so we're going to have 97,000 defects, right? But that part is easy. I let you to do that when you do the homework question. Here we are more concerned about the stigma level of the process. The stigma level of the process is Again, we already talked right away at the beginning of the class, right? We use this general definition as the following. So 1 minus a dBu plus 1.5. But remember, the dBu is the same as a P of D here, right? That's the probability of being defective here. So we would put the numbers in as the following. Norm dot s dot inverse 1 minus the 0.09693, right, and add with that 1.5. So this equation has two separate parts. No, Theo, 9.7% multiplied with 1 million will be, yeah, you are correct, Theo. Yeah, 10% out of one. No, not 10 million, 1 million. In the manufacturing context, they normally talk about 1 million as a benchmark. So out of 1 million units, how many units are defective? Okay, so 10% of 1 million will be 100,000, right? Defects. Or in this case, to be a little bit more specific, 9.7% out of 1 million means 97 defects. I'm sorry, 97,000 defects. Think about it, right? It's a huge number of defects. All right, so the sigma level that we have right here is composed of two parts, the first and the second. Oh, see, you are very fast. Okay, so how do we have that level, right? Somebody please try this number and share what number you got. The first part of the equation right here. I do not ask for the whole thing yet. I only asked for the first part of the equation. So everybody please try it and share, right? So what would be the first part of the equation here? What C shared is the total with the 1 plus 5. But I would like you to go through this as a steps, okay? So that we understand more about the calculation. Okay, so Marco and Peyton, okay, good. You have the 1.299, or Michael, you round up to 1.3. That is correct. And of course, C earlier, if you subtract the 1.5, you also see the 1.30. All right. Rose also had the same thing. So Rose, Christopher, you all agree that's a good thing, right? Okay, so we have 1.3 for that part of the equation, but remember at the end we have to add with 1.5. So at the end, the final answer is 2.80, right? So how about that 2.80 sigma level? When you say that our our process has a sigma level of 2.8, how does that sound? It sounds bad, right? Yeah. 6.0 means near zero defects. 6.0, right? 6.0 means out of 1 million units, we only have 3.4 defects. But here it's not 6.0, it is 2.8. It's a number very low relative to 6.0. So this 2.8 normally means that the process is bad, okay? So that's the, okay, so now let's try to sketch the number. The sigma level, right? It might sound technical, but actually it is just a number that signals about the quality of the process. So why is that? Because if we sketch it out, it's going to look like the following. That's a standard normal distribution right here. Okay. The standard normal distribution has the mean at 0, and then we cut the right tail so that the right tail is our probability of defects, which is 0.09 693 in our case, or 9.7% effective, right? And of course, on the left-hand side, where the P of G, the probability of being good is 0.9, 0307, right? Okay, so we cut the right tail so that the right tail equals the probability of being defective. And then we got that 1.30, right? So the Excel equation that you see in that equation right here is a 1.3, right? The whole thing here is a 1.3. It's just a lookup function for us to pin down that blue point. So after we have the blue point, we would add with 1.5, and then we have the red point, and the red point is 2.8, and that 2.8 is our sigma level. All right, so the sigma level of the process is at 2.8. And here's how we would say about it. So the process is operating at 2.8 sigma, right? I would not be proud if I say that my company is working at 2.8 sigma, because that 2.8 sigma sounds low. Okay. Okay. So that's the first example where we go through the event tree to understand the logic behind the outcomes, then calculate the P of G, the P of D, and then calculate the sigma level, and now we have a sigma level to communicate how good the process is, right? 2.8 sounds low, so it's hard to sell our product if we are operating at 2.8 sigma. Let's continue with the second example, and that will help you with question 24. Let me show you the second example. It goes as the following. Let me share. In the medication delivery of a drug, prescribing doctors sometimes make mistakes overseeing allergies of the patient or interaction of multiple drugs. You know what? Whenever you visit a doctor's office, they will give you a questionnaire where they ask you if you have any allergies, if you have any medication right now, right? Because when the doctor prescribes any medication, they will have to see if that intended medication have some allergy impact on you, or does that interact with other drugs and makes something bad for you, right? So that's why they always ask you for allergies and current medication information. But sometimes, you know what, doctors, they miss those information, right? And that's bad, because the wrong medication will go home with the patient and then might cause some allergy or some bad reaction inside the patient, right? So you know what, from time to time, the patient just die because of the allergy. So actually, we talk about a very serious process here, right? So next, a 3-step medication delivery process is used once the doctor has requested a wrong medication. So in this case, we assume that there's a wrong medication in the first place. And our process is used to catch the wrong medication, right? But sometimes the system might miss the wrong medication. So the first, the nurse delivering the medication needs to pick it up from the pharmacy. The pharmacy catches 70% of the mistakes. Next, the nurse sometimes double checks the medication with the attending physician, which catches another 80% of the mistakes, right? For simplicity, we assume that different parties here have different, independent check probability. So the pharmacy catches the mistakes 70% of the times. The nurse might check with another doctor, right? Attending physician might be another doctor, not the doctor that prescribes the medication. So the new doctor here, the second doctor here might catch the wrong medication made by the first doctor, right? So 80% of the time. And finally, sometimes the patient herself alerts to the nurse to the medication problem. So, however, that only happens 50% of the cases, right? So again, we have 3 stations along the line. The wrong medication will go through the pharmacy, will go to the nurse, and go through the patient themselves, right? So the question is, how much do we catch? How much do we miss? Right? The probability of being defective and the probability of being good. So let me work on this with you. To make it clearer, we need to draw the event tree. Without it, it's really hard to think about how what the outcomes are and then how to calculate the probabilities of the outcomes, right? Okay, so we have the second example. In this case, we talk about catching a wrong medication. Right, and this is module 5, slide, I think 72, right? Okay, so again, the first thing we should do is we understand it first by drawing out the event tree. So here, the wrong medication, we have to go through 3 stations, right? Station 1 is the pharmacy. Station 1 might miss it or might catch it. There are 2 possibilities, right? If we miss it, we call that as defective. If we catch it, we call that as good, right? So defective here means miss, and good here means catch. Okay, so that's might happen. That's what might happen at the first stage. The pharmacy might miss it or might catch it. And now we are at the second stage. Then the nurse might also miss it, or might they also catch it, right? So we'll draw the 2 possibilities here. And we assume that the second station is independent of the first one. Right, so miss here, catch here, miss here, catch here. And the third stage is the patient themselves. So that's a station number 3. Right, a real life situation can be adapted to this model like this, so that we can apply to many cases in real life, right? And then the third station, we either miss it or we catch it, miss, catch, miss or catch, miss or catch. So miss, we call that as D, catch is G, defective, defective and good, defective again and good again. Right. So if you look at the tree, there are 8 possible overall outcomes, or the 8 fruits right here. And it looks like before. But you know what? The logic beside this tree is totally different from the logic that we see in the previous tree. Okay, so I would like to ask the whole class regarding the first branch right here. Okay, is that defective or good? Where defective means we missed the wrong medication. and good means we catch the wrong medication. Okay, so I see a lot of D's already. Good, you are correct. In this case, we can say the following: all three parties missed the wrong medication, right? So at the end, the answer, I mean, the outcome, the overall outcome here is we have a D, defective. And that's bad because the patient will go home with the wrong medication. If something happens, then the hospital will have to pay millions of dollars in compensation, right? And think about it, as a manager of a hospital, you don't want that to happen at all. You don't want this outcome to happen at all. Okay, so we are done with the first branch. I would like to ask everybody about the second branch. What do you think about it right here? Is that good or effective? Okay, so at least I see two cans here. And that's understandable because it's confusing. It's not that straightforward at all. This topic is confusing. Of course, we need more practice to be efficient, right? But at least now I see two cans. That's okay. We are learning. Okay, so let me interpret what happens here. At the first stage, we missed the wrong medication. At the second stage, we also missed the wrong medication. But luckily, the patient themselves caught the wrong medication, right? So if one party caught it, then they will go back to the pharmacy, ask the doctors, things like that. So they will fix the wrong medication, right? So now at the end, the patient will go home with the correct medication. So the outcome here is actually the good outcome, right? So that's the logic. We have to think about what happens here before you can determine if it is good or defective. Not to mention, sometimes it is confusing when we talk about defective and good here. The names by themselves are confusing, right? So in this case, at the end, we catch the wrong medication. And with that, we can fix it. And that's why we call this as a good outcome. So we have a good outcome here. How about the third one? How about the third branch that you see here? Is that good or defective? We try that one more time, and then I think that everybody will know how to do it, right? Okay, right now I still see two cans. That's fine. We do another round of learning here, right? Okay, so it looks very scary right now, right? We have defect, good, and defect. But if we talk about the context, then we would call these as the following. We missed the wrong medication at that station. We catch the wrong medication at that station. And then we missed the wrong medication at that station. But then as long as somebody caught the wrong medication, then they will gotta go back and rework on it and fix it, right? Nobody wants to have the wrong medication going through the process. So as long as we have one good, then the final outcome will be good. So in this case, right, the correct answer here is a good outcome. So we have good number one, and then we have good number two. And by the same token, we're gonna have good number three, because we have miss, catch, and catch. The next one, we have catch, miss, miss. That sounds bad, but actually that's another good outcome, because at least that station caught it, right? So if they catch the wrong medication, then somebody will fix it for the patient. And then the next one, by the same token, right, we have catch, miss, and catch. then this whole thing will be good, G5. The next one, catch, and miss, right? Catch, and miss. So definitely somebody can fix the wrong medication. So that's another overall catch right here, or good outcome right here. And then at the end, where everybody catches the wrong medication, right? So we have 7 good outcomes and only 1 bad outcomes in this tree. It is the reverse of what we have earlier. Even though at first the 2 trees look similar, right? But remember, behind the tree, the connection between the parts of the tree are different. So that's why the fruits or the outcomes are totally different from before. Okay, and now to calculate the probability of being good and defect later on, we need to know the sizes of the branches, right? So just look at the question. 70% mistakes that the pharmacy catches 70% of the mistakes. So it means that we would write 0.7 right here for catching, and for missing, we're gonna have 0.03 right here, right? At the second stage, we catch the mistakes 80% of the time. So we're gonna have 0.8 right here, 0.2 right here, 0.8 here, 0.2 here, right? And then at the third stage, we catch the mistakes 50% of the time. So the 50 catching is right here, and the missing is the remaining, which is also 50%, right? It's just a coincidence that we have 50 and 50%. Okay, so and beside those, you can put all the 0.5, 0.5, 0.5, 0.5, all here, right? They are consistent with what we have in the first instant right here. Okay, so right now we have the complete tree that shows all the possible events or the possible outcomes through the process, right? So it's totally different from the tree that we got earlier, even though they might have the same number of branches, but the branches are different, right? Big or small, and then the fruits are totally different. Okay, so now we have the tree complete, and then let's do the calculation. The calculation itself now should be easy for everybody, so let's do it as a following. So the strategy here is we calculate the P of D first, because we only need to do that one time. So P of D at the first stage. I'm sorry, we have to multiply. Adding will be totally wrong. So the probability of missing at the second station times the probability of missing the wrong medication at the third station, right? And if you look at the tree, we just multiply that 0.3 with that 0.2 with that 0.5, right? You just trace along the first branch. And then the overall outcome is going to be 0.03. Roughly speaking, we talk about 3% defective. Right? That's the PFD right there. And then we flip it. The probability of being good is supposed to be P of G1 plus P of G2, P of G3, 4, 5. But it's a very long line. It's so painful to write all of these out. Okay, but of course, we use a shortcut one more time, right? And the shortcut is the 2s up to 100%. So we just take one minus the other. Then we're going to have what we want. So we take 1 minus that 0.03. Then we have 0.97% of 0.97 probability of being good. So it means that we talk about 97% good, right? Unit. Okay, 97% is better than the process that we have earlier. Earlier, we only have 90% good, but this one, 97%, right, is better than the process that we have earlier. In terms of the sigma level, we expect what? We expect this sigma level to be higher than the sigma level that we have earlier, because our process produced fewer defects than before, right? So the sigma level is going to be norm dot s dot inverse 1 minus dpu, or p of d in this case, and then add with that 1.5, right? We take norm dot s dot inverse 1 minus 0.03, add with 1.5. And this is basic, right? We just use Excel to calculate this part of the equation. That's going to be what? 1.9. 1.9, and then we add with 1.5, right? Then at the end, our sigma level is 3.4. So remember, earlier we only have 2.8 because we have nearly 10% defective. But in this case, we talk about only 3% effective. That's why the sigma level needs to be higher than before, right? We have a better process than the process that we had earlier. But if you think about this 97% catching, meaning that we missed 3% of the time. And that 3% might be enough already. Somebody might go home with the wrong medication and bad things might happen, and the hospital will have to pay millions of dollars in compensation, right? That's not good for everybody. That's not good at all. So 3.4 might not be good. 97% might not be good for a very serious process like this. As a manager at the hospital, we might want to do more than this, right? Okay, so in the homework, I also ask you to draw the sigma level. So we just draw it one more time here. We draw the standard normal distribution like that, the 0 in the middle, and then we cut the right tail so that it is the P of D, right? 0.03 or 3%. It might sound small, but this is a serious process. Then we might want to be even smaller than that, right? So this number, if you calculate that in Excel, is going to be 1.9, the one that we saw earlier. And then we add with 1.5, then our sigma level. Our sigma is 3.4 right here. Right, so that's a sigma. And at the end, you just make a statement. I encourage, because I encourage you to say it out loud. If you know how to say it out loud, you really understand it, right? So we can say that the process, this is a wrong medication catching process, okay? The process is running. Earlier, I used the word operating, but here we can use another word without changing the meaning at all. So the process is running at 3.4 sigma. So if you are the director or the manager of this hospital, might be over time we have to invest in the process and make it better, right? So that we can reduce the P of D and increase the sigma level of the hotel, of the hospital. Okay, so with that, I would like to end the class here. Thank you for joining me. Have a great weekend, and I would like to see you back next Monday. Right, so remember the remainder of homework 3 is due next Monday. I hope you are ready.
Thank you, Professor.
Thank you. Happy. That is correct, Sophia. When you redo it, I do not look for right or wrong. I only look for the efforts. And you know what? I will revise the Canvas option so that you can see what you missed on Canvas in the first attempt. And the second attempt is for your learning. So I do not look for right or wrong. I only see that you do all the required work of the video. Okay, good. So I hope everybody is doing well. I would like to close the meeting at this point.